Assalamualaikum and
Waalaikumsalam.
Dr.
I'm sorry for the delay because I have a quite bad internet line here. All right, so today we're going to learn the last part of the chromatography topic, which is the use of organic analytes chromatography based method for calibration and validation. All right. Can you see this?
Yes.
All right. So for every analytical technique, we need to calibrate and validate the data, right? Question is to, to set the instrument for the correlation between the response and the concentration, because the aim is for the quantitative analysis, we want to know the amount of the analyte concentration, right? So it needs to be as accurate as it can, right? And as precise as we can do, all right? So first, calibration methods commonly used in analytical chemistry to find the quantitative relation between two variables, for example, response and the concentration, and to determine analyte concentration in sample. The calibration curves are normally linear. However, not all the points are located on the drawn straight line due to the random error. And then regression analysis can be done on the data to see how good the linearity of the data is. Okay, so method of least squares. All right. As a measure of the correlation between two variables, for example, the signal and the concentration, and to estimate how good the experimental points fit a linear curve. Right, the value of R lies in the range of -1 to +1 to 1. All right, -1 to 1. Right, the closer the R value to 1 or -1, the better the correlation between Y and X. So the perfect one is either 1 for positive correlation or negative for the negative correlation. Right, the perfect of the acceptable R is 0.999. That is the perfect word for the correlation. All right, so acceptable fit of the data to the regression line. Okay, the example of correlation coefficient. Right, so R square equal to 1. Perfect, right? All are in the line. Okay. So R equal to +1, perfect positive correlation is all points lying on the straight line. But seldom you get perfect correlation. It's very, very rare. It's very perfect to get this one, right? Normally due to error, right? The random error, we will get. So how much is acceptable? 0.9962, is it acceptable? 0.9809. Okay, more significant error than with R square equal to 0.996. Right, this is the perfect one for negative. Right, sorry, this is a very poor one, right? Points are outside of the lines. So the R square is equal to 0.0120 112. So this is very bad. Method, okay, the direct or external method, okay. The most common method used are one or more external standards which containing a known concentration of analytes. We call them external because we prepare and analyze the standards separate from the sample, right? The external standards, meaning that we prepare a set of known concentration of solution, right? Without using any portion of the sample. We prepare it separately from the sample, okay? Normally we run the calibration first. Of course, we need to run the calibration first, right? To draw a straight line of the correlation coefficient, right? To get the perfect R square. So that when the instrument already know, right? Remember, I told you all the analytical instruments are normally what? Quote unquote. Anybody can tell me? All the analytical instruments are? I want to hear the word. Yes, right. Remember my class, okay? So we need to teach the instrument, right? So that they know how to measure the concentration. So we do the calibration, right? We prepare a series of standard concentration, right? With known concentration, okay? Increasing, right? Not similar concentration, but with increasing concentration, right? And then we teach the instrument, right? So if you find this kind of response, you detect this kind of response, for example, in chromatography, that it is the signal of in the chromatogram, right? If you find this, so this is the concentration, right? In the chromatogram is represented by the you know, area chromatogram, the area of the, what is represented by area of the, anybody? Right, never mind, we go first. Most convenient when a large number of similar samples to be analyzed. Okay, prepare a series of standard solutions, analyte solution with known concentration, and we plot the analyte versus analytical signal. Use signal for unknown to find analyte. Perfect one. Okay, so y is equal to the signal. Okay, the y axis is for the signal, x is for the concentration, m is for slope, and c is intercept. So now, what is the intercept? Sorry. Zero, right? The intercept now, zero. Because we prepare from the first concentration is 1. For example, this is ppm. So the calibration, in the calibration plot, we assume that zero signal give zero, represent zero concentration. So we start with 1. Okay, 2, 3, 4. Sorry about the pen. Okay, and 5. Okay, so this is the relationship between the response and the concentration. So we plot it. Previous, we prepare the concentration, a series of known concentration separately from the sample. But what about the internal method? We prepare a set of standard solution for analyte as with the calibration curve method, but add a constant amount of a second species B to each solution. So what is species A, species B? Prepare a plot of species A divide by species B versus analyte versus the A, the analyte in the calibration plot. Species A and B must not produce signals that interfere with each other. Usually they are separate by retention time. In analytical sample size, position, or metrics limit the precision of a technique. May correct for certain type of noise. The resulting measurement will be independent of sample size and position. The internal standard calibration method, right? Why do we need to prepare two type of compound, all right, in one calibration for detection of for example, we want to detect the concentration of X, and the standard is S. Okay, let us read the note. Okay, now known amount of a compound different from analyte added to the unknown. The compound with a known concentration but different with the unknown sample, meaning that the different peak will be appear, not the similar peak. Signal from unknown analyte is compared against signal from internal standard. Relative signal intensity is proportional to concentration of unknown. Right. Valuable for sample and instruments where response varies between runs. Calibration curve only accurate under condition curve obtained, and relative response between unknown and standard are constant. Widely used in chromatography to analysis. Okay. Remember this keyword. It is this method, or we call as internal standard calibration method, right, is useful if sample is lost prior to analysis. Okay. The area under curve proportional to concentration of unknown and standard. Okay. Right. From this response factor, and C for the concentration. Okay. What is mean by known amount of compound different from analyte added to the unknown, right? Meaning that we know that the standard that we're going to calibrate, we're going to put inside the the sample, okay, is not similar with the peak appeared for the sample. But this one is unknown, all right, this one is standard. Okay. Okay, so it will appear separately. Okay. The relative signal between the relative signal intensity is proportional to concentration of unknown. What meaning by relative signal intensity, okay, is proportional to concentration for sample and instrument where response varies between runs. Calibration curve only accurate under condition curve obtained, and relative response between unknown and standard are constant. For these two peaks, all right, we already know the difference between two peaks, all right. So there will be a response factor there. Okay. Wait for a while. right? Okay, so now the purpose of this internal standard calibration is to measure the concentration of the sample. Okay, but we are using okay. Again, okay. Now we put the standard of an known concentration standard. Okay, to the we add into the sample and we run. Okay. So analyte from the sample is appear here in the chromatogram. Okay. So we put inside the sample a standard that appear the peak appear separately from the okay, and then okay, this method is very useful if sample is lost prior to analysis. Okay. In this technique, which is the internal standard, we have an equation like this. All right. The peak area of the unknown, okay, x, okay, divided by concentration of the unknown is equal to the f, okay, it's a factor, all right, and times the peak area of standard divided by the concentration of the standard. Let us see the solution containing a 0. You can do this together, right? Because when you write it, you will, you will understand better, right? A solution containing 0.0837 molar of X analyte and 0.0666 molar of S, the internal standard, give peak area of AX, right? Jot down the important, okay? Give the peak area of AX equal to 423 and AS 347. To analyze X in an unknown sample Z. Okay, now the sample is Z, right? But we want to analyze X inside the Z sample, right? To analyze the X in the unknown sample Z, 0.146 molar of S was added to 10 ml of sample Z, and the mixture was diluted to 25 ml. If a chromatography spectrum with area AX equal to 553 and AS equal to 582. Find the concentration of X in sample Z. Okay. First one, in a solution contains 0.0837 molar of X and 0.0666 molar of S, give peak area of this, right? And here we have the light and the internal standard, right? Now we want to analyze the analyte X inside in the unknown sample Z. Okay. Okay. The answer is step 1. We determine the F first, right? How to determine F? We use the first. We have from the known concentration of X and known concentration of S, it's a standard. We have also the peak area. So we use that information to find F. Now we have F. Okay. Remember, Cx is the concentration of analyte X, and Cs is the concentration of this internal standard. All right. Peak area of analyte X, and As is the peak area of internal standard S, and F is the response factor. Now we have the response factor value. Okay, go to step 2. Right now, we determine the concentration of analyte X after the dilution. Okay, so if Cs is equal to 0.146 molar times 10 equal to 0.0584 molar. So determine the concentration of analyte X after the dilution. And then we have 0.0572 molar of Cx. And determine Cx in the unknown sample. Okay. Now we have Cs 0.0572 molar times the dilute. Then we have 0.143 molar. Is it not finished? Guys, after step 3, when we determine the Cx, we determine the Cs, all right? Now how to find the in the sample Z? Do you have any idea? We have the factor already, okay? The concentration of X after dilution, okay? Right? Now, the concentration of X in sample Z. Who has the idea to share on how to determine Cx in the sample Z? We have all the value now. You can share. I will use the whiteboard. You see the whiteboard? Can you see the whiteboard now? In the chat, I give the link to for you to share the whiteboard from your own. In the chat box, please use the link. I want to share the calculation to calculate the amount of the concentration of CX inside the sample Z. You have the slide, right? You have the notes already, right? I have given you the e-learning, right?
Yes.
But some part are missing, right? So you have the idea already, okay? You have the idea, okay? From 1 until step 3. So how to find the CX in the unknown sample? Divide by CX equal to F AS divided by CS, okay? Just put all the amount and then you will get the concentration. You can share the whiteboard, okay? Okay, now I have Anis Irfan, KCX7, who's that? And Nadra and Noor, okay, inside the whiteboard. You can write down your calculation and you can share after this. Don't put search, put calculation step and also the answer. It's okay if your handwriting on the whiteboard is bad. In this idea, the relative response between the unknown and the standard are constant, are always constant. All right, who want to share? Irfan, you want to share? We have which Irfan want to share? Right, Anis want to share?
Sir,
Yes.
dekat slides, dekat step 3, dia kata CS tapi dia guna consideration of CX.
Dia salah information eh. Itu dah CX kan? Itu dah CX ke? Step 3 is already CX or CS?
CX.
The calculation.
CX.
CX. So, what's the answer?
0.143.
All right. So that is already the answer. All right. That is CX. Okay. So you just copy that in your whiteboard. All right. So you got the idea why we need to do this internal standard calibration method, and it is widely used in the chromatography technique. Okay. Because the factors, okay, response factors are always constant, okay, and then the you know we have to make sure that if we dive the analyte X, but for the instant standard of the different compound also need to be diluted, so that the response factor F will right. Normally, this internal standard is quite confusing for the students, because especially for now, because we are learning online. Okay, do you have any question about this internal standard? Let me share the slide again. Stop sharing. Right. For the first step, okay, from the given information in the first paragraph, okay, we have concentration of X and also S, okay, and also we have also the peak area. Okay, so we now step 2 is for the concentration of X after dilution. Okay, now we calculate the CS value first, right? And after that, we just put in the equation. We know F, we know AX, right? We know also AS, and now we know the CS, and of course we know how to calculate the CX. Now we need to determine CX in known sample. So this is CX. Sorry. Okay, this is CX, not CS. It said that the mixture gave a chromatography spectrum with area X553 and is 582. All right. And from the previous information, it gives us the amount of analyze X, right? To analyze X in an unknown sample Z, 10 mil of standard. We know the volume of the standard S and the concentration, right? And we know added to 10 mil of samples that we know the samples that is 10 mil, and the mixture was diluted to 12 mil. Right. So from that information, we know of X now. Okay, for step 3, we determine the CX in the unknown sample. Okay, so how? What is this? 0.0572 is concentration of X after the dilution. Okay, and why we straight away times the volume 25 mil divided by 10 mil. Why we need to do that?
Because we need to identify in Z samples. So mixture bagi dengan sampel.
without dilution, right?
Yeah.
Because this is in the diluted sample. Wait for a while. Okay, because of the dilution, right? But we want to know the original concentration in sample Z. Am I correct? Am I correct? Because the information of AX and AS is for the diluted version. Okay? The diluted version. So we have in the diluted version. So to calculate the CX value in the original version, so we need to times these things we call as the dilution factor. Okay, dilution factor. Method is solution with a matrix interference or effect will give a different signal compared to a solution containing purely the analytes. Okay, remember a solution with a matrix interference. Okay, our sample have a matrix interference or effect will give a different signal compared to solution containing purely the analyte. Okay. Now, to analyze the analyte that we want in the sample, we have an interference from the matrix. So how to do it? Consequently, standard calibration, okay, external standard calibration, not internal, method cannot be used to accurately determine the analyte concentration. Right? So the standard addition is devised to overcome a particular type of matrix if that will otherwise to a bias result. Okay, so how to do it? First one is add one or more increments of standard solution to sample liquids of the same size. Okay, we have a we prepare a series of a standard calibration, but now the first step is, for example, we want to prepare 5 concentration of the calibration, but first step is we must use the sample itself. We divide the sample itself in 5 different container. Okay, 5 different flask. Okay, right, and then we put with a similar, right, and then we prepare right the standard calibration solution using the sample that we have divided, all right, volume. Okay, and then we prepare the plot of analytical signal versus volume of standard solution added or concentration of the analyte added. The x-intercept of the standard addition plot correspond to the amount of analyte that must have been present, all right, in the sample. Counting for the dilution. Okay, always count for the dilution. Okay, the standard addition method assumes that the curve is linear over the concentration range and the y-intercept of calibration curve will be 0. Okay. Do it. For example, the standard calibration for the external method. Okay, a series of 5 zinc standard solution. Okay, let's say you analyze all solution using AS instrument. Okay, we have the but this one not using chromatography. We just assume we use AS for the standard calibration. It's similar one, but just different response. Okay, so we have this standard calibration for external, the normal one, right? We prepare a series of standard solution with an increasing concentration. So when we analyze, we get the linear graph, and then let's say you have tap water sample containing zinc, sample A, right? This is standard addition method. Okay, we have the unknown solution, okay, the sample, okay, and then we have the stock solution, right? The standard, okay, with known concentration. So we prepare a series of a standard solution with an increasing concentration using the sample itself. Okay, so the sample should be in same volume, but we need to increase the standard standard solution volume. So that at the end we know the concentration of the standard in every solution, but we don't know what is the beginning of the analyte concentration inside the sample. So how we this method that's why we call this method is standard addition. We add the standard solution into the sample. All right, that we plot no longer intercept at the zero value of x, because during the beginning, okay, x plus 0 ppm, okay, so that the x plus 0 ppm meaning the sample itself without the addition of any standard solution, and then x plus 1 ppm, this one x plus 0, and then we have x plus 1, x plus 2, and so on. Okay, x plus 0 is a sample itself without any addition of the standard, so the intercept must not be 0, because there are some analyte inside the sample that we need to know. Then we have a series of concentration with increasing value because we add the standard solution, right? So we plot the graph, the intercept, okay, the intercept at y equal to 0, okay, then we extrapolate, okay. First step is we measure, so we analyze, and second step is, all right, we just analyze, okay. Second step, what is measure at concentration, okay, and then we plot the graph, okay, for every concentration, and then for the intercept at y, you just extrapolate the graph until it intercept at x-axis, and this value of intercept, okay, at x-axis is the concentration of the analyte inside the sample. But what about the negative value? Just make it positive, right? Meaning that the value of concentration x is equal to, okay, x intercept, sorry, the value of intercept x. Oh, very bad handwriting. Okay, ignore this one. So the concentration of Cx, okay, is equal to intercept, okay, intercept of, what happened to my pen? Intercept of x-axis. This is a concentration, okay. So right, Okay, xi divided by xf plus sf equal to ix. All right, what is this? It's not, you know, it's not complete as well. Okay, I think this is plus. I think it's not complete. All right. Okay, xi is unknown initial concentration of analyte before adding standard. Xf is unknown concentration of analyte after adding standard, and Sf is a known concentration of standard after adding standard. Right. Directly. Okay. So ascorbic acid or vitamin C in 50 ml sample of orange juice was analyzed by HPLC to get a detecting peak area of 178. Okay, 50 ml, and we get 178. A standard addition of 0.4 ml of 0.279 molar of ascorbic acid increased the peak area to 335. Find the concentration of ascorbic acid in the juice. Right? We have V equal to V0 plus Vs, okay, for 50 ml plus 0.4. So we have 50.4, and XF is V0 over V. So XF is equal XI. XI is the analyte that we're gonna find, okay. Times 50 over 50.4, right? So SF is equal to SI times Vs over V. So we have SF is equal to 0.279. Okay, times 0.4. Okay, where is 0.4? Here. Okay, divide by 50.4. So see, this is the calculation for SF. Okay, this is the SI. Okay, and then we have 0.00221 molar. This is the SF. So we can now calculate the XI, right? So we put it in the calculation. So we have XI equal to 0.0249 molar. Okay. XI meaning that X initial, XF is X final. Okay. X is the analyte unknown and S is the standard, right? Ascorbic acid in 50 ml sample of orange juice was analyzed HPLC to get a detecting of 178, right? A standard addition of 0.4 ml, okay, 0.4 ml of 0.279 molar ascorbic acid increased the peak to 335. Now we have the information. Okay, 50 ml at 0.4. So we have total volume of 50.4. So X final, okay, is equal to X initial times volume of volume, okay, and divide by final volume. But we don't have both of the XF and XF, right? Okay, and then we have SF. Okay, when we put all the amount the value that given, we already have SF. Okay, and then we just replace in the equation. So we get initial concentration of the light. Okay, now we're gonna learn. We learn about the type of calibration. We have three type calibration. Okay, external calibration, internal calibration, and also standard addition. Right. Now we move to validation. Confirm that the analytical procedure employed for a specific testable for its intended use. The process of verifying that a procedure or method yields acceptable results. And then the purpose is to defend validity of the result and demonstrate method is fit for the intended purpose. And responsibility of the laboratories. Based on the evaluation of the method performance and the estimated uncertainty on the result. So how? So analysis of using this standard method. Two methods, and then recovery study by spiking standard that we know, an amount of the analyte that we know, to the blank metric, which then the null is obtained and compared with your data. There's a lot of parameter in the method validations. All right, we have LOD, limit of detection, LOQ, limit of quantification. Okay, and then we have a recovery. We have a linearity. Okay, recovery, acceptable recovery is 80%. Okay, equal or larger than 80%. Okay. Less or equal than 20%. This is the amount of recovery. Okay, sorry. Okay, so we have linearity, sensitivity, activity, precision, and accuracy. Recovery. So recovery studies by spiking or adding a known amount of the analyte to the blank metric, which then the signal is obtained and compared with your data. So percentage of recovery is the analyte concentration in spike assay divided by analyte concentration in the sample, okay, and times 100. Or weight of analyte in spike assay divided by weight of analyte in spike sample times 100. The linearity, linearity of an analytical procedure is its ability to obtain test result, okay, sorry, that are directly proportional to the concentration of the analyte in the sample. Linearity is also demonstrated by the analysis of various concentration of the analyte across the intended range and represent graphically. A statistical analysis of the data is usually required, such as calculation of regression line using this method or least square. A minimum 5 concentration is recommended. Remember, we do calibration plot. That is linearity. Okay, and then triplicate. Okay, use a calibration or standard curve. Okay, and then triplicate. Okay, meaning we have to measure 3 times at least, and then the regression, the R square, is larger than 0.0998. Okay, what about accuracy? The degree of agreement between measured value and the true value, which may not be known. Therefore, it is the degree of agreement between measured value and the accepted true value. What about the precision? Okay, degree of agreement between replicate measurement of the same quantity, right? Precise and accurate. So repeatability of the result. So expressed by standard deviation, the coefficient of variation confidence interval about the mean value. How similar are values obtained? Exactly the same way. That is the basic thing of precision. And then useful for measuring deviation from the mean, right? This kind of what we call this, the target, okay, the arrow target. Okay, this is how we want to explain about precision and accuracy. So this one is precise and accurate. Okay, precise because it is every value is quite similar, and accurate because the degree of agreement with the true value. For example, the true value is in the yellow circle. So when we analyze, we always get close to the true value, and the repetition of the analysis is not accurate. This is the most perfect one. But this one is inaccurate. It's not close to the true value, but the repetition of the analysis is not so far from each other, right? And this one is not precise and not accurate. This one is accurate but not precise. Okay, some of the analysis that have been done is vary in the true value. Okay, but repetition of the analysis doesn't give the precise result because it so far from each other. But this one is not accurate, okay, because not one of the none of the analysis have been vary in the true value, but and also far from each other. The repetition of the analysis is far from each other, so it is inaccurate and imprecise. So what about the range? The interval between the upper and lower concentration of analyte in the sample for an analytical procedure that has suitable level of precision, accuracy, and what about ruggedness? Okay, ruggedness of an analytical method is the degree of reproducibility of the test result obtained by analysis of the same sample under a variety of conditions. Okay, this is ruggedness, robustness, similar with robustness, meaning that the ability of the instrument to sustain the result from the analysis even in different condition, right? For example, in the weather, okay, if in the bad weather or in the good weather or in the different day or with the different analysts, okay, for today I analyze the sample and tomorrow Irfan will analyze, okay, does the instrument give the similar result, precise result to each other or completely different, right? And then from lab to lab, today I use this instrument in my lab and tomorrow Anis use this instrument in her lab. So what about the result? It is rugged or not? This different from each other or not? If we use the same method and we use different instrument, how about the result? Is it similar, precise, or accurate and precise or not? Okay. For chromatography, if we change the column, what about the result? Okay. And then if we change the reagent kit, okay, what about the result? Accurate or not accurate, precise, not precise, right? So if we change all these conditions and we have the quite similar result or precise and accurate result, so that the instruments or the method is rugged or robust. Okay. In Malay we call tahan lasak. Okay. Dan the is meaning that in whatever condition we have the same or quite same result. Okay, the robustness of an analytical procedure is a measure of its capacity to remain unaffected by small but deliberate variation in method parameters and provides an indication of its reliability. Ability to assess unequivocally the analyte in the presence of components that may be expected to present, such as the impurity, the degradants, or the excipients. So this is we call selectivity. Okay, meaning that if we analyze our analyte in the sample, the impurities or degradants doesn't affect our result because our instrument select only the analyte to be analyzed. Now we have limits of the, okay, LOD is the lowest amount of the analyte which can be detected but not necessarily quantitated. Okay, this is only detected by instrument but not quantified by the instrument, not calculated by the instrument. Okay, so S over N is equal to 3S blank, where S blank is standard deviation for the blank and S is the slope or the sensitivity. For example, the absorbance divided by the concentration. Okay. Signal, S is signal divided by the N. Okay. by the value, the true value. Okay. For example, we analyze the blank. Okay. Okay. S blank is a standard deviation for the blank. Okay. And S is the slope for the sensitivity, right? Or LOD also can be calculated with this calculation. 3 times the standard deviation of the blank. We analyze the blank. For example, our blank is distilled water. Okay. So we have the standard deviation for the distilled water concentration. Okay. Times 3. Okay. So 3 times standard deviation of the blank divide by slope. Okay. The absorbent versus absorbent divided by concentration, so that we have LOD, the limit of the detection. Blank solution was analyzed giving peak area values as tabulated in the table. A standard solution of 1.5 ppm aspirin gave 0.095. This means the signal. Okay. Calculate the LOD. So LOD is 3 times SD blank divided by slope. So equal to 3 times 0.02. Where we get this value? Here. We have the signal is 0.02. And then, okay, the signal is 0.05 and the concentration is 1.5. So we have the LOD is 0.095 ppm. Quantitation, LOQ. So LOQ is the lowest amount of analyte in a sample that can be quantitatively determined with the precision and accuracy for assays of low level of compound in sample matrices, example impurities and or degradation products. Okay, remember the low of analyte in sample that can be quantitatively determined with the precision and accuracy. Right, so what formula? So S over N equal to 10 standard deviation of blank, or LOQ is equal to 10 times standard deviation of the blank and divide by the slope. Let's say, okay, for this similar example, can you calculate what is the LOQ? So what is the LOQ for this? And time the deviation of the blank. So 10 times what?
0.02 bagi dengan 0.095 bagi dengan 1.5.
0.02 then
0.02
0.002, okay.
bahagi dengan 0.095 bahagi dengan 1.5, dia punya concentration
95.
1.5.
And how much you get?
0.3158. 0.315
ppm. Okay. Now you can see that LOQ is higher than LOD. You can see that? What we conclude now, if even the instrument can detect at 0.095 ppm, okay, but the concentration that can be calculated, right, that can be verified, or can be what we call that, can be verified by this instrument, starting from 0.315. If you analyze using this instrument and you get value of a 0.091 ppm, and you present this value in your result, saying that in sample A, you have 0.091 ppm of vanilla X. Is it acceptable in the report? Can you give the idea? Does it acceptable in the official report, saying that you detect 0.091 ppm of vanilla X, right, in the sample A, okay, and the LOD is 0.015, let's say 316, right? So it is acceptable? No, because the acceptable value that can be reported from this instrument is starting from 0.315 quantitation, right? Quantitation means that the quantity, right, that can be officially, okay, detected by this instrument starting from this value. This formula is acceptable around the world, okay? But what is the LOD information used for? This is only to know the ability of the instrument itself. What is the lowest detection that, what is the lowest concentration that the instrument can detect? Detect, not quantify, right? For us to quantify, to give the quantity, right, the acceptable value is using that equation, and for this case 0.3158 ppm is the lowest value that can be acceptable presented by this instrument. You get it? You get it? Understood? In every analysis, in every analytical report, we need to report how much is the value for LOD and LOQ before we present our result. Okay? Okay, this is the precision, okay, estimated by the deviation from the mean, okay, of the multiple analysis. Okay. Intermediate precision expressed within laboratories variation, different days, different analysis and different equipment. Okay. For example, we have this table 6, a demonstrate of the intermediate precision of HPLC assay result for progesterone. So HPLC system 1, we have two systems, system 1, system 2, and different sample 1, sample 2, sample 3, and different analyst 1, analyst 2. Okay. The value. Done by performing replicates. Okay. The purpose is to ensure that the method is working properly to reduce the S sample error. The sample. Identical sample analyzed under different conditions. Equipment, analysts, or different laboratories. Right, quite similar. In relation, we use different instrument, different analysts, okay, and also it expresses the prediction between laboratories. This is the collaborative study. So that's all for the sharp 1 p.m. Okay, that's all for the sample analysis and also the calibration and also the validation of the data for this chromatography method. For the calibration, similar with the spectroscopy method. Okay, known standard solution, okay, because the keyword is our instrument stupid. We need to teach the instrument. This is a concentration according to the signal, right? And then for this one, we have one more type of the standard for the calibration. Okay, for spectroscopy, the only the external calibration and also internal calibration. But different for chromatography, we have also the internal calibration method, which is we put the we put the compound that different from the analyte. Okay, but we know for standard calibration previously that we put a similar compound with the analyte as the calibration, but for internal standard calibration we put different compound from the analyte, but with the constant. So what is the constant factor? Okay, the constant factor is here. For example, the distance between these two peaks. Okay, right. The distance between these two peaks and also the peak area. Okay, different, meaning that we increase the concentration. Okay, and the factor is being remain. Okay, this widely used in chromatography and useful if sample is lost prior to analysis. Okay, if we have the complete information or the incomplete information, so just fill in the equation. Okay, for example, if the first information gives you all the value of concentration and also the peak area, so you have to find the F, and then missing part of the according to the questions. Okay, for example, for this CX, we know the CX in the diluted version, so we need to times the dilution factor so that we have the original concentration of X in the sample. Similar with AAS, we prepare a series of standard solutions, okay, using the sample itself, meaning that we separate a similar volume of sample inside, for example, 5 series of different concentration of analyte. For example, for this time we use vitamin C as well. So we use a sample, okay, itself a standard solution. So that after that, in we have value in terms of part of the axis y, and then we extrapolate axis of the x-axis, and then the intercept of the original concentration inside the sample. So why we need to standard addition if we only want to know about the intercept? So we just put we just analyze x plus 0 ppm at y-axis, then we extrapolate. But how you want to extrapolate? Either this way or this way, okay, or far away, this way, okay. That's why we need to have a series of standard addition concentration, okay, so that we know the direction of the intercept. Okay, so that the intercept of at axis y, and then we extrapolate, we have an intercept of axis x, and that is the concentration. Okay, we just put in positive value. Do we have a concentration in negative value? An extra question for you. Do we have a concentration in negative value? We don't have. All right. The concentration must be 0 or more. Okay. That is for today. Do you have any question?
No, doctor.
And when does this equation use?
Standard method.
Standard method. Standard addition method, right? For example, if you want to find the x final is equal to x initial times the final the initial volume divided by final volume, okay, initial volume, okay, the vs is the standard added, okay. We find, if you want to find the SF, okay, so SI times Vs, the volume of standard added, divided by the V itself, okay. So XF, okay, unknown concentration of analyte after adding standard, okay, and SF is known concentration of standard, okay. Normally in the question they will give SF, right, or vice versa, or they give this information and find SF. Okay, so based on this equation, so right, what is this actually? Ix, and this Ix, what is this actually? The missing part, because the image is similar with this one. What is this actually?
Ix plus S. Ix plus S.
X plus
S.
this one, right? Okay. Unknown concentration of analyte and known concentration of the standard. So Ix is unknown initial concentration of analyte, okay, before adding standard. All right, do you have any question? Okay, we can see from this example, we know the V, okay, and then XF, we know the equation of XF here, and we know the equation of SF here. Okay, and we put the all the value inside this equation. So SF is replaced by this value. So XF is replaced by this. Okay, so that we have the similar subject here. We have XI. Okay, so then we can find XI. The question we play with the value, play around with the value. Okay, it's quite mathematical, but you need to formula. Okay, this is only acceptable for the chromatography.
Sir, kalau dalam
Yes.
final, nanti in this subtopic we focus on calculation or we need to memorize also the procedure about this method?
If you ask me about memorize, of course, all lecturer will not recommend the student to memorize. Okay, please understand. Okay.
I mean the procedure for standard addition methods. They in the final always
Normally
keluar.
calculation. Okay. For the standard addition, normally in form of the calculation. Also for the internal standard. Okay. They will ask in the calculation. Normally, chromatography, the calculation part is about this equation. And also the TLC part, right? TLC part is calculate the RF value, right? Okay. And then for this one, method validation, normally we have recovery questions. Okay. For example, we have okay, we prepare this. So for example, 100 ppb. For example, this is for chromatography. Okay, here we have a standard solution. We have 100 ppb of ascorbic acid, and then we prepare the sample. This is a sample. Okay, we use the process to prepare the sample from the beginning, from the, for example, from the digestion with the sample, and then we we filter the sample, and then until we analyze the sample using HPLC, the concentration that we get. For example, we have acceptable recovery, I say that plus minus. This is meaning that plus minus plus 20%. Okay, meaning that if you have we know that the concentration is 100 ppb for ascorbic acid, right? We analyze. If we get 80 ppb, is it acceptable? Yes, acceptable. It is not acceptable. What? And 10 ppb. We know the concentration that we put is and 10 ppb, 110 billion, so it is acceptable. 120, of course, acceptable. And what about 122 ppb? It's not acceptable. minus 20%. Okay, meaning that you get less or more 20% by the original concentration, it is acceptable. But what about more than that? Meaning that you get more than 20%, meaning that you get 122 ppb. So it's not acceptable. Or less, or you have you analyze 79 ppb. Simple one. Okay. So learn how to calculate the LOQ and the LOD. Right. Never mind. We will do some revision after this. Okay. Okay. Do you have any question? No question? Or in the chat room? You have any? No. Right. No question anymore. Okay. What we gonna learn after this? After this topic, we have finished the chromatography technique. Okay, we learn from basic principle, and then we learn TLC, HPLC, GC, and then we learn the sample preparation and sample analysis. So now what? We have finished chromatography technique. We will come to the final topics, right?
Revision, Doctor.
Yes. What?
Next class do revision. Final
Yes.
revision.
Right. Before we go for revision, we have two other topics, right? Let me share with you what is it. We have two other topics, which is the first one is a statistical related to chemical analysis. Okay, t-test, f-test, and q-test, and type of error. Okay, and then we have also the gravimetric and the classical chemical analysis, which are the gravimetric and volumetric. For all this topic, I will only give you the video for you to watch. Right? I will give the lecture in form of video for you to watch. Then, okay, I hope that you will finish to watch all the video. Okay, and then we will meet again on this coming Thursday for discussion of those videos. And if we complete before 1 hour, then we start our revision on this coming Thursday. Or if you have a lot of questions that I need to explain for the methods, for the classical and also the chemical analysis, statistics, and then so we need to complete that first. And then next week we will do revision for the final exam. Okay, it depends on how you understand the video will give you in the e-learning. In this coming Thursday, we discuss if we have time. So we start the revision straight away on this coming Thursday. Understood? Can you get it?
Yes, Doctor. Doctor, we have quiz 4 in week 15.
Yes. Yes, actually we have quiz. Sorry, not mentioning that. But I plan to do the quiz not this week, maybe next week. just the quiz in the e-learning. Okay. Don't worry about the quiz. Okay. From what I have observed, all of you, you can understand the method I have taught you very well. Okay, so quiz 4 is not so hard for you. Remember, for quiz, the question will not be, you know, you need to think a lot for the question. No, the question will be straight away. Okay. All right. If you don't have any question, I will when I already upload the video inside the e-learning for these 2 chapters. And chapter classical method, we have to volumetric and volumetric, right? And I will notice you in the WhatsApp group, right? Okay, if you don't have any question, can we stop now? All right, thank you, and thank you. Okay, see you on this coming Thursday.
All right, Doctor.
Oh, we have not done quiz 3. We only have 2 quiz.
Yes, Doctor. Only 2 quiz.
So I will take the marks from the assignments. We only have quiz 4 of it, so quiz 3 based on the assignments, right? Thank you so much, and see you again on this coming Thursday. Bye bye.
Thank you,
Assalamualaikum.